month or so of reorganizing. And today, I want to talk about something that I think is incredibly exciting. It is the question that most computer architects, no matter what the machine, parallel architecture, supercomputer, anything you want to talk about, don't even know exists. And that question is, how is it possible for computation, which is an abstract process, it's symbolic, it's something in a mathematician's head, how is it possible for that to occur or somehow be implemented in physical digital hardware? Um, this question lies at the foundation of all information processing, and it's worth having a look at because the results have some interesting implications for a unifying theory of everything. That is, physics, matter, information, computation, and ultimately including consciousness. So, how can you leverage your way into a unifying theory of computation and physics? Well, how about exploiting the common temporal factor involved in both? Everything that happens physically happens in time, physical time. Everything that happens computationally happens in computational time. Now, the temporal aspect of computation is very key because algorithms are classified according to their temporal behavior. And there are two broad categories. One is the exponential algorithm, like, how many different ways are there for a traveling salesman to go, from the starting point to his ending point, passing through, umpteen other cities. That's a so-called exponential time problem. And that means it's pretty bad. And there are, by contrast, polynomial time problems. I don't know, FedEx. How many paths does there have to be among various cities to deliver from one to the other? That's just polynomial time. It's relatively easy. Anyway, the point I'm getting at here is not about the classification of algorithms, but rather to point out that if the algorithm takes an amount of time that increases exponentially with the number of cities, let's say, then the amount of physical time that the physical process implementing the algorithm takes as a function of the number of cities is also exponential. Now, there's nothing terribly shocking about that. It's kind of obvious, even though you may not get what I'm saying. It's to anybody who understands what I'm saying, it would be obvious. So why do I point it out? That's a siren. I have to deal with these all day long. 6 flights above Lexington Avenue in Manhattan. Now, I point it out because there's a very important isomorphism between physical time and computational time. What do these two things have in common? Whatever takes place in physical time is change. Whatever takes place in computational time is change. What changes when you run an algorithm? The data is what changes. That's why you run the algorithm. The whole point is to change the input data set to an output data set. What changes when a physical process occurs? Well, basically, matter is what changes. And the thing that changes it is energy. Okay, so let's say you have, you squeeze a marshmallow. The marshmallow is matter. It's what changes. How did it change? By virtue of the energy, applied as a force, by squeezing the marshmallow with your hand. So, physical time and computational time are both there as a kind of medium in which change takes place. The nature of the change in the case of the physical is energy, changing matter. The nature of the change in the case of the computational is algorithm changing data. So there seems to be a kind of correspondence between algorithm on the one hand and energy on the other, and between data on the one hand and matter on the other. And this is much more than an appearance. It's an underlying isomorphism, and I have to tell you, I haven't seen this anywhere. Once you see it for what it is, if I had a diagram, this would be a lot easier to get. It is, forgive me for so saying, I'm going to kick myself, it's obvious. Just as algorithm is executed in computational time, so energy is expended in physical time. Moreover, just as matter exists in physical space, so data exists in computational space. A better word for computational space is probably memory. So the whole point of this is that there's an underlying fourfold structure to computation that parallels in very significant ways an underlying fourfold structure to physics. Okay, I'll go over that again. The fourfold structure of computation is algorithm, data, computational space, and computational time. The fourfold structure of the physical universe is correspondingly energy, matter, physical space, and physical time. I'm going to do this again with a diagram, and it's going to be a lot clearer. This isomorphism, this parallel between physics and computation will prove instrumental in coming up with a unifying theory of not just information and physics, but also consciousness. So please, stick around. It's going to get more exciting and more interesting. I'm Eric Lindell. Thank you for your interest.